Welcome. So the topic we will be discussing in this lecture is vector computation. So before getting into the actual concept, let us try to understand first of all what is meant by vector computation. Vector computation means performing some operations on vectors. Okay, what is a vector? You might have learned in physics or something else like vector. Okay, so vector, there are two terms, right? One is a scalar, the other one is a vector, right? We say there is something called as scalar, and there is another quantity which is called as vector. Okay, so vector scalar means it has only a one entity, right? It has only one entity. Okay, whereas in a vector you have more than one entity. You'll have more than one entity. Okay, so in the sense you can say that array is also a vector. Okay, array is also a vector because array contains what? Array contains more than one element. If you have an array a of 10, it is a single array, but it is not having one element, it has 10 elements. Okay, so maybe like this it may have so on and so forth up to 10 elements. Okay, so this is actually a vector, right? But normally conventionally vectors are represented something like this. Okay, in this way we represent vector. Okay, so here array is represented like with one row and multiple columns, whereas conventionally vectors are represented as a as a single column with multiple rows. Okay, so you can say that this is a vector, this is a vector. Okay, right. So vector computation means, say for example there is a vector a with 5 elements, 1, 6, 7, 12 and 20. Okay, there is another vector b with some other 5 elements. There is another vector b with some other 5 elements, say 2, 18, 21, 36 and 60. Okay, say now we want to add these two vectors and we want to create another vector. Okay, so that we call it as vector c. So vector c is nothing but it is just an addition of vector a and b. Then vector c will contain what? 1 plus 2 3, 18 plus 6 that is 24, 21 plus 7 28, 36 plus 12 48, 20 plus 60 18. Okay, so this is called as vector addition. Why we call it as vector addition? Because two vectors were added, right? Now how to add this? Normally in a normal program also you can add. In a normal program when you add, how will you add? Probably you can write a C program or a Java program or a Python program to add to these two vectors and to create a destination vector. Okay, so but how we add? We add individual elements. We add individual elements which is called a scalar. We take each scalar quantity and we will add. Like this 1 and 2 will be added and this 3. Then 6 and 18 will be added, 24 will be created. Then 7 and 21 will be added, the result 28 will be created. Then 12 and 36 will be added and then 20 and 60 will be added. Okay, so this is actually, even though these are vector, this type of addition is actually a scalar addition. It's not a vector computation, it is a scalar computation. Okay, but there are computers which can process this vector as one entity. Okay, it just adds this one entity with this another vector which is another entity and produces an output. So it performs all these things in just one shot or in one clock cycle. Okay, whereas if you use a normal general purpose computers, for each operation if you take one clock cycle, then it will take 5 clock cycles to complete this addition, because there are 5 elements or 5 set of scalar quantities to be added. But if you do this using a vector processor, it will complete it in one clock cycle, because it is not going to do any scalar addition. It is going to consider this entire thing as one vector and it is going to add this with another vector, and it is going to create a resultant vector. So this is called as vector computation. So you may be asked, what is the need for this? There are a lot of need for this. In most of the scientific applications, this kind of data will be available, which are called as vector data. And here we have discussed vector with 5 entries, each vector with 5 entries, but each vector may contain hundreds or thousands of entries, and one vector should be you may have to process these vectors as a whole stretch, as a bundle. Okay, and if you apply scalar computing there, then then this processing speed will be very low. Okay, so that is the requirement, or that is the motivation behind learning this topic, vector computation. Okay, or even if you take an image, what is an image? An image is nothing but a collection of pixels. If you take any image is a collection of pixels. Okay, so there is a separate course called as image processing, where where you'll be learning like what is an image, how to improve the clarity of this image, if this is dull, how to improve it, or if there are some damage in the image, how to remove those damages. So in image processing also, normally there will be lot of operations which will be done on the image. Okay, so there also you cannot apply scalar computation. If you apply scalar computation, then then the processing speed will be very slow. So you may want to even merge two images, and you want to create a resultant image. Okay, so in that case, what is more appropriate is vector computation, right? So this is the brief introduction to vector computation. So with this, let us start. So there is always need for computers to solve mathematical problems of physical processes. Okay, that is, physical process means that is the processes which are appearing in the nature. People always want to study the nature. Okay, that is existing from, what do you call, how long, since when humans were there in the earth. Okay, so people want to learn how the nature behaves. So with the advent of computers, people want to take the advantage of computers, and through that they want to understand the behavior of the nature. Okay, but if you want to understand the behavior of the nature, then for that you have to collect huge amount of data, and you have to process huge amount of, and you have to perform lot of processing. All these involves heavy mathematical tasks. Okay, so these are some of the examples: aerodynamics, seismology, meteorology, atomic, nuclear and plasma physics. These are some of the areas where a lot of mathematics were involved, and precision is more accurate here. They need very accurate results. Okay, it is not that some approximate result will do, no. And also it involves lot of floating point arithmetic operations. Okay, so these type of applications are generally can be called as continuous field simulation. Field simulation means what? Simulation means it's a model of a real-time environment. So whatever happening in the real time, they create a simulated environment of that, and those scientists will be learning, or they will be trying to understand the behavior of the nature through this simulation. And all these things involves a lot of mathematics, and high precision is required. Okay, so conventionally supercomputers is used for these tasks. So normally this will be done by supercomputers. Okay, but the problem with supercomputers is its cost. They are the supercomputers cost is very high. Okay, and normally supercomputers are available only in some big universities in US. Okay, or in some government organizations, right? In India, there are some supercomputers like Param. Such supercomputers are available. Mm. I think it's available only with government organizations like CDAC. Okay, probably they will be using it for defense related research. Okay, so otherwise, getting a supercomputer or seeing a supercomputer itself is a difficult thing. So so the problem is, of course, supercomputer can do these calculations, but its cost is a primary concern. Okay, and another reason is supercomputers are not designed only for parallel vector computation. Supercomputer is a general purpose computer. Okay, supercomputer is a general purpose computers. That is, it can perform any task. It can perform any task, and they have many processors, and it can also perform high precision calculation, all those things. But the problem is with its cost. Okay, and these are not custom designed for vector computation. They are general purpose processors, right? And also there is a constant demand on supercomputers to increase the performance in spite of its rare availability. Okay, so here comes array processor or vector processor. So here comes array processor or vector processor, which are designed to address the need of vector computation. Okay, so these vector processors or array processors, what they do in the sense, they are specifically designed to work on vectors. Okay, these processors are custom designed. You can say that these processors are custom designed to work on vectors, whereas normal processors, they work on scalars, whereas these processors are custom designed to work on vectors. Okay, and these processors can be configured as a peripheral device in a normal computer. Say for example, already you have a computer, okay, which is a normal computer, right? And now you are doing some research or something, and that demands lot of vector processing. Without vector computing, you cannot do anything. Now you cannot go for a supercomputer. Okay, supercomputer may cost several crores. Okay, so what you have to do, you can just purchase array processor. Array processors are peripheral devices, remember. So inside the motherboard there are some slots. These slots are called as PCI slots or ISI slots. So using these slots, to these slots you can connect the array processor. As a peripheral device you can connect. Okay, now if any high computation tasks which involves vector computation, where more where one or more vectors has to be processed, in such cases those high computer high those jobs which demand high computation, that will be just transferred to these array processors. These are array processors which are connected as peripheral devices, and this will take care of that, and this can do it in no time, right? Okay, so the topic we are going to discuss in this lecture is about array processors or vector processors, right? So this is the reason why array processor comes into picture, because for performing such mathematical calculations, which requires high precision and such huge mathematics, you cannot go for supercomputers because of its cost. So we have array processors which are custom designed to for vector computation, and they can be configured as a peripheral device in a normal computer, right? Okay, so this is a typical example, like how an vector addition works. So if you perform, so there are two vectors. This is a vector A, this is vector B, and we want to add these two vectors, and we want to create a resultant vector C. Now if you use scalar addition, you have to use how many operations? 1, 2, 3. You have to use 6 individual operations. But when you perform vector addition, it is just one operation. This is one vector, this is one vector. Just these two vectors will be added, and the resultant vector will be created. Okay, so that is what will be done by a vector processor or an array processor. So now let us try to understand the difference between scalar processing, vector processing, and parallel processing with an example. We are going to discuss three things. What are the three things? We are going to discuss about scalar processing, vector processing, and parallel processing. Okay, so this example is on matrix multiplication. So I guess you remember the logic for matrix multiplication. So if the let us assume that the matrix A contains n rows. Okay, the matrix A contains n rows. Okay, we are not bothered about it columns. Say it contains C1 columns. Okay, say the matrix B contains n columns. Okay, or let us say all matrix contains n in both the matrix contains n rows and n columns. Okay, Now the resultant matrix C will have n rows and n columns. Okay, right? Are you getting? Otherwise, if you want me to be more specific, if matrix A contains R1 rows and C1 columns, okay, row into column, right? And if matrix B contains R2 rows and C2 columns, okay, then the resultant matrix will have R1 rows and C2 columns, right? Okay. So the number of columns in the first matrix should be equal to number of rows in the second matrix. Okay, right? So fine. So if the matrix A contains this n into n rows and n columns, and B contains n rows and n columns, then the resultant matrix there will be n rows and n columns. Okay, and what is the logic? The logic is something like this. If you write a for loop, if you write a equivalent C coding, how it will be? The equivalent C coding for matrix multiplication, how will you write it? Just a minute. Yeah, so it will be something like this: for I is equal to 0, I less than n, I plus plus. Okay, it is actually number of rows in the first matrix, and then for j is equal to 0, j less than n, j plus plus. Okay, it's actually number of columns in the second matrix, right? And then for k equal to 0, k less than n, k plus plus. Okay, here what we do, c of I comma j is equal to c of I comma j plus a of I comma k into b of k comma j. Okay, so that's what we are going to do. So this is the logic, this is the core logic. C of I comma k, c of I comma j is equal to c of I comma j plus a of I comma k into b of k comma j, right? Okay, so that's what we are going to do. Okay, so this k will repeat for this k will repeat how many times? This will repeat for number of columns in the number of rows in the second matrix. Okay, this will repeat for I will repeat for number of rows in the first matrix, j will repeat for number of columns in the second matrix, and k will repeat for number of how many rows in the second matrix, right? So here is the normal logic which we follow for scalar processing, but this is a Fortran program, so the program is little different. So instead of for loop in Fortran, there is a loop called do loop. Do loop is similar to for loop. So you can just understand that this is a for loop which is ranging from for I is equal to 1 to n. Okay, here there is a 100, which means that where this loop ends, this loop ends here. Okay, in C we use open bracket and close bracket to end. Okay, whereas in Fortran we have to use this label. So this loop starts here and it ends here, right? So wherever this label 100 comes, there it ends. So this is the outer loop. So inside that there is another loop, do 100 j equal to 1 to n. So this is j loop for j is equal to 1 to n. Again this loop ends where? At 100. So it starts here and it ends at 100. Okay, so this is outer, this is inner. Then here we are assigning c of I comma j equal to 0. Here also you can write that inside the for loop, inside the j loop, you can write c of I comma j equal to 0. So initially c of I comma j is set as 0. Then the next k loop, do 100 k equal to 1 to n. So this k loop starts here, it also ends here, right? Then this is the logic, c of I comma j equal to c of I comma j plus a of I comma k into b of k comma j. This is multiplication. Okay, there is a mistake, right? So this is how normal in a scalar processing we do, right? Now we are going to see how this task will be done in an vector processing system. Okay, assume that your computer has a ability to vector process. That is, it can process one vector at a time. Okay, it can process one vector at a time. Vector means what? One column. One entire column is called as a vector. So it can process one vector at a time. Then if vector processing is supported by your system, then this same program can be written like this, because Photon also supports vector processing. Okay, that is, but when you write the program, you should be careful. See, in a vector processing machine, if you write the program in scalar style, you cannot take the advantage of it. You're getting big, then it will still work in scalar style, and you cannot take the benefit of that. If you are writing the program in a vector processing machine, then accordingly the program should be restructured. So this same program is restructured like this, so that we can take the advantage of vector processing, assuming that our system has vector processing capability. Okay, now let us see the code. So here, this is the outer loop, the I loop, which is ranging from 1 to n. This is the inner loop. This is not, sorry, this statement you see, this is actually a vector processing statement. C of I comma j equal to 0 0, j equal to 1 to n. This is one statement we are giving. What does it mean? See, this statement, what it says in the sense, actually it's a single statement. C of I comma j equal to C of I comma j equal to 0 comma 0, j equal to 1 comma n. What does it mean? When I is 0, okay, when I is 0, it is talking about all the columns of the resultant matrix. All the columns of the, when I is 0, it refers to, sorry, when I is 0, it refers to 0th row. Okay, I is 0, it refers to 0th row. Let us assume the resultant matrix contains 4 columns. The resultant matrix contains 4 columns. So n is what? 4. Okay, so n will range from, you can say, either 0 to 3 or 1 to 4. Let us assume 1 to 4. As of this style, it is 1 to n. In C, we go from 0 to n minus 1, but here it is given as 1 to n. Okay, so when I is 1, when I is 1, this loop, what it is doing? C of I comma j equal to 0 comma 0, j equal to 1 to n. Then this entire row, it will be filled with 0. It will be filled with 0. Are you getting? Because I is 1, then j ranges from what? 1 to n. So first time j will be what? 1 comma 1, 0. Then 1 comma 2, 0. 1 comma 3, 0. 1 comma 4, 0. But this is not doing individually. For explanation, I am telling 1 comma 0, 1 comma 1, all those things. But actually this is done as one instruction. It's not, there is no repetition here. But here it is a repetition. Here it is a repetition. This every time this will become 0. I mean, this statement will execute. For example, if the resultant matrix contains 3 rows and 4 columns, then this statement will execute 12 times. Then only all entities will become 0. But here that is not the case. Here this will execute, when it executes for the first time, in the first row all the columns will get 0. When it executes for the second time, in the second row all the columns will become 0. When it executes for the third time, in the third row all the columns will get 0. Right? Okay. So this is how it works. Right? Because it is what? It is a this is called as vector processing. Okay. Right? So this is with respect to C. Similarly, if you, this is with respect to this particular statement. Okay, so next statement you see, do, again there is a do loop, do k is equal to 1 to n. Now the k loop is repeating for 1 to n. Again here we are writing C of I comma j equal to C of I comma j plus A of I comma k into B of k comma j. Again we are saying j equal to 1 to n. So j equal to 1 to n means what? When I is 0, when I is 1, at one stretch, it is going to calculate the result of all these things. It is going to calculate this value, it is going to calculate this value, it is going to calculate this value. Are you getting? Right? Similarly, when I is 1, this will be calculated. When I is when this will be calculated when I is 1, this will be, all these things will be, these things will be calculated when I is 1, all these things will be calculated when I is 2, okay, all these things will be calculated when I is 3, and all these things will be calculated when I is 4. That is the meaning, right? When I is 1, when I is 1, it will calculate what? J is ranging from 1 to n. So C of I is 1, okay, so 1 comma 1, then 1 comma 2, then 1 comma 3, then 1 comma 4, which means uh, in the first row all the uh, yeah, when I is 1, sorry, I have mentioned here wrongly. Okay, it is not the entire column, it is going to calculate one row, it is going to calculate one row. Okay, so initially all these are 0, 1 2 3 4. Let us assume the resultant matrix contains 3 rows. So when I is 1, when I is 1, it is going to calculate this value. Okay, say, so this value is what? C11 in the resultant matrix. This is C12, this is C13, this is C14. Okay, because I is same 1, but C is changing, but all these are calculated in one stretch. Are you getting? Because it provides vector computation. Similarly, when I is 2, when I is 2, all these things will be calculated. Which one? C21, C22, C23 and C24. When I is 3, these things will be calculated. 31, C32, C33 and C34. Right? Okay. So this is how vector processing works. So now, so if you in scalar processing, it needs how many computations? 12 computations. For each one there is one computation, but when you use vector processing there is only 4 computations. For each row there is only one computation. Okay, so this is how this program will be written in vector computation, right? Now let us see how the same program can be written in parallel processing, right? In parallel processing, what you have multiple processors. In vector processing, you have vector processing, you don't have uh, see, here also we may have multiple processors, but in fact it is not actually the multiple processor. It is in vector processing, the uh, the vector processor is added as an, the vector processor is a specially designed processor. So if you recall, vector processor is a custom designed processor. Here it is there, right? Array processor, vector processor is a custom designed processor which are used for only for vector computation. These are custom designed for vector computation and they are added as peripheral devices. So they are not general purpose processors. They are not general purpose processors. They are good at performing vector processing. That is, whenever you have a vector, in processing that they are good, but they cannot be used as an ordinary processor. Okay, if you try to use a vector processor as an ordinary processor, it may not perform well. It may not perform well. Okay, so there is a difference between vector processing and parallel processing. Parallel processors are general purpose processors. These are general purpose processors. Okay, right? So, mm, so next what we are going to discuss is parallel processors. So with parallel processors, we are going to assume that now the computer is having more than one processor. It may have 4 processors or 5 processors, okay, and all these processors can uh, all these are general purpose processors. These are not vector processors, and all these processors can work independently. Okay, in that context, so if the system is having more than one processor and if it has a parallel processing ability, okay, then how this program can be written using again photon. So now if you see, in the outer we have this do, first we have this loop j loop. First we normally first we have I loop, but here it is quite different. First we have j loop. For do 50 j equal to 1 comma n minus 1. So where is this 50? This 50 is here. So it means that this loop ends here. This loop ends here, right? And this loop is repeating for how many times? N minus 1 times. It is not repeating for n times. Okay. So if n is 5, okay, as usual, let us assume that A matrix size is n cross n and B matrix size is also n cross n. So the resultant matrix size is also n cross n. Okay. So if n is if n is 5, okay, or if n is 5, then the outer loop will execute for 4 times because it is n minus 1. Okay, and inside this loop what we are doing, fork is used for what? In Linux we have learned fork is used to create a child process. So it fork 100, so it will create a child process, and this child process will start executing from line number 100. Are you getting? It will create a child process, and this child process will start executing from line number 100. So this loop will execute for how many times? N minus 1 times. So how many child process we are creating? N minus 1 child process we are creating. So these three statements, what it will do, it will create n minus 1 child processes. So if n is 5, this will create 4 child processes. It will create 4 child processes. Okay, right? So it creates 4 child processes. Okay, now each child process will execute this. See, each child process will execute this. Okay, what is here? Do 200 I equal to 1 to n. So 200 starts here, it ends here. So now here I loop is here. I is equal to 1 to n. C of I comma j equal to 0, 0.0. That is, each j loop will execute this separately, right? Because I mean each child corresponds to j loop. Each child corresponds to the j loop, and so there are n minus 1 child process. All these n minus 1 child process will execute this part. Okay, and they will set the respective j as 0.0, and then there is a k loop. Do 200 k equal to 1 comma n. C of I comma j equal to C of I comma j plus A of I comma k into B of k comma j, right? See here how it works in the sense, say let us assume that again, say the resultant matrix contains 4 rows and 3 columns. Okay, sorry, 3 rows and 4 columns. So initially it is nothing. Okay, even the 0 is not there. So now let us see how 0 is filled first in the resultant matrix. That part let us try to understand. That will help us to know how it works. See here, there are n minus 1 child processes were created. Okay, so n is what? Number of columns. So here what is the number of columns? Here we are assuming that there are 3 rows and 4 columns. So the number of columns is 4. So n is equal to 4. If n is equal to 4, this loop will repeat for how many times? 3 times, because it is n minus 1. So it is going to repeat for 3 times. Okay, right? It's going to repeat for 3 times, right? But remember one thing, after repeating for 3 times, see this for loop will repeat for 3 times. So it is going to create 3 child process. It is going to create 3 child process. After repeating up to n minus 1, where it will come? Control will come down. Here it will come. Okay, and then it will set j equal to n. So j equal to, at that point what will be j? At that point what will be j? J will be 4. Okay, because already that outer loop has repeated for 3 times. That is, it has gone up to n minus 1. N minus 1 is 3. So when it, after coming out, after 3 it won't continue, right? It will come out. It should come out. So j will become 4, right? When j becomes 4 also, this will execute. Here we are not stopping. This will execute. Okay. So this is the parent process. When j equal to n, at that time, this is the parent process. Parent process also execute the same thing. But apart from the parent process, there are 3 child process. They are also going to execute the same thing. Okay. Right. Now let us see what the first child is going to do. So first child, when it is coming here, its j value will be 1. Its j value will be 1. Okay, and what it is going to do? Do 200 I is equal to 1 to n. So this loop is going to repeat for, its j is 1 for the first child. This is child 1. Child 1 means j is 1. Okay, when j is 1, child 1 is created, right? So, and it is going to repeat the this I loop for n times. What is n? Okay, this n is, let us assume it is uh, okay, or let us assume this also 4. Okay, 4 rows, right? N is 4. Okay, so it means the number of rows is 4. It is going to repeat for 4 times. Okay, but j is 1. J is 1, remember. Now what we are setting, c of I comma j equal to 0. So what is I? I is 1. I is 1. J is also 1. So 1 comma 1 is equal to 0. Now this location will become 0 just. Okay, then another loop. Do 200k equal to 1 to n. So now k loop is coming. So here we have I loop. Okay, now k loop is coming. K loop is also repeating for n times. Okay, then for k loop what we are calculating, c of I comma j. So what is I? I is 1. What is j? J is also 1, equal to what? C of I comma j. What is C of I comma j? I comma j is 1 comma 1. So C of 1 comma 1 plus A of 1 comma k. Currently k is 1. Okay, k repeats from 1 to n. Okay, A of 1 comma 1 into B of k comma j. What is k? K is 1. Okay, 1 comma 1. All this will be added, and that result will be stored here. Okay, that is C11 will come here, right? Now again this k loop should complete, right? K loop should repeat for 4 times. So next iteration, what it will calculate? In the next iteration, what it will calculate? Okay, k should repeat for how many times? K should repeat for 4 times, right? So here we are saying do k equal to 1 to n, right? So again it should repeat. Okay, so yeah, so once again it will continue. Okay, that is c of, okay, see, just I have elaborated this. So assume we have an array of a of size 4 comma 4 and b of size 4 comma 4. Okay, then the resultant matrix, how will you calculate? This is that first element. This first element in the resultant matrix will be what? It will be a11 into b11 plus a12 into b21 plus a13 into b31 plus a14 into b41, right? Similarly, second element will be a11 into b12 plus a12 into b22 plus a13 into b32 plus a14 into b42, so on and so forth, right? So during this one iteration of the k, it is only multiplying what? A11 into b11. So this k will repeat for how many times? 4 times. Okay, this a11 into b11, that result is now in c11. Okay, so in the next iteration it will be what? C, again it will be c11 only, because I and j are not changing. C11 equal to c11 plus, now this c11 contains what? A11 into b11. Okay, now what it will calculate? It will calculate a12. Okay, I is same. I is same. Okay, I is same, but j is changing. Okay, a12 into b21. Okay, so here I have written wrongly. A12. This is a12. This is a13. This is a14, right? This is a11 into b11, a12, like that, right? So this will be multiplied with this, right? Similarly, second round, second value, this will be multiplied with this, right? Okay, so now we got what? Now we got a11 into b11 plus a12 into b21, but still that is not sufficient. Again k will repeat for another time. Are you getting? Again k will repeat for another time. So in the next round it will calculate up to here, then in the next round it will calculate up to here. Are you getting? So this is for one iteration of k loop. Okay, during the second iteration of ki, during this is for all iteration of k, that is one iteration of I. During the second iteration of I, it will calculate the second value. I will repeat for 4 times. During the third iteration of I, it will calculate the third value. Okay, during the fourth iteration of I, it will calculate the fourth value, right? Am I correct? Okay, that is I, j is not changing. Okay, j is what? J is only what is j? J is, we are assuming j is 1. Okay, j is 1, I is changing. I is changing. Sorry. So we are not calculating this way. We are calculating I is changing, right? So if I is changing means what? J is only 1. So this is child process 1. J is 1. I is changing. I, in the first iteration of I loop, I is 1, second I is 2, third I is 3, fourth I is 4, but J is same. Okay, so the first child process will calculate the all the values corresponding to the first column. It will calculate this. Okay, if you call this as x1, then it will calculate x2, then it calculates x3, then it calculates x4, right? Similarly, the second child process will calculate all the values corresponding to second column. Third child process will calculate all the values corresponding to third column. Okay, right? Fourth, there is no fourth child process. That fourth is the parent process. Parent process will calculate all the values corresponding to the last column. Are you getting? So this is how it is going to work. So each of this is a separate processor. Try to understand. Each child is going to use a separate processor, because here we are discussing what parallel processing. So first processor will be calculating all these column values at one stretch. That is the first column result at one stretch, and the second processor will calculate all these at one stretch. Third processor will calculate all these at one stretch, and fourth processor will calculate all these at one stretch, and all these are going on in parallel. Right? Okay. So this is how this will be done in parallel processing, right? Okay. So the difference, I think you are able to understand. In vector processing, what happens in each round? In each round, it calculates what? One row values. Okay. First round this row, second this row, third this row, fourth this row. Okay. I mean in vector processing. Whereas in parallel processing, first processor will calculate the result of first column. Second processor will calculate the result of second column. Third processor will calculate the result of third column. All these will be controlled by child processor. This is child 1, child 2, this is child 3. And the last processor will do the last column. Okay. So if this is child n, then the last nth processor will take care of this. Okay. And all these things can take place parallelly. All these tasks can take place parallelly, right? Okay. So this is how things works in vector processing and parallel processing, right? Now let us discuss different approaches for vector processing, vector computation. There are generally two approaches. One is called as pipelined ALU, the other one is called as parallel ALUs. So what is a pipelined ALU? In a pipelined ALU, you will have only one arithmetic logic unit, but this arithmetic logic unit may have multiple functional units. Okay, it may have multiple functional unit, like functional unit 1, functional unit 2, functional unit 3, and functional unit 4. Okay, or more than that. Now these can be used for pipelining. Say if there is a job 1 comes, now job 1, let us assume it should go through all these functional units 1, 2, 3, and 4. Now first it will go to functional unit 1. Once this functional unit 1 is completed, it will go into functional unit 2. When job 1, when it is in functional unit 2, job 2 can be in functional unit 1. Are you getting? When job 1 is in functional unit 2, job 2 can be in functional unit 1. Okay. Similarly, some other job, say job K can be using functional unit 3. Some other job L can use functional unit 4. Okay, because these are free, right? So when similarly when job K has finished using this functional unit, okay, then job 1 can come to functional unit, can start using functional unit 1, right? If job L has completed all these tasks, it will be releasing functional unit 4. Now job K can come here. Okay. So this is called as pipelining, which we have already discussed. In pipelining, there will be only one arithmetic logic unit, but this arithmetic logic unit may have multiple functional units. So what happens in the sense, this can be used in a pipelined operation to improve the performance. And also another with respect to vector computation, the pipeline, if they have vector registers, if these pipelines are attached with vector input and output registers, so these are not ordinary registers, these are vectored input and output register, okay, then its performance can improve. Okay, say for example, uh, you want to perform a vector operation, which is A is equal to B plus C, where A is a vector, B is a vector, and C is a vector. So it's not scalar. So A contains n elements, B contains n elements, C contains n elements. All these elements you want to add, and you want to add all the elements of B and C and put it in A. This is what you want to do. Now you don't want a normal register which can hold only one value. You want a vector register. So if you have a vector register, if it is a vector register, it can hold n values. Now all the values of A can be kept here. This is another input register. All the values of B can be kept here. Now this pipeline can take it, and according to its convenience, it can process and proceed. Right? Similarly, finally, it will keep the output in the vectored output register. Okay. Right? So this approach is called as pipelined ALU. The next approach is called as parallel ALU. In parallel ALUs, you have more than one arithmetic logic unit. There is only one processor. The system does not have more than one processor. The system has only one processor. There is only one CPU, but there are more than one arithmetic logic unit. So now really you can perform more than one operation parallelly. Okay. Now if you have 3 ALUs, you can perform 3 operations parallelly. But again these 3 ALUs can be pipelined. Again these 3 ALUs can be pipelined. Okay, that we will be discussing with an example. Right. Okay. So let us assume that a typical operation, a typical arithmetic operation, it involves all these stages. It should go through all these stages. So normally in floating point operation, it should go through all these stages. What are they? Compare the exponent, shift the okay, the significant amount of time, add, and then normalize. Okay. So this is with respect to floating point addition or subtraction. All these are required. Compare the exponent. We have to compare the exponent part. Then shift the significant. That is the normal number should be shifted so that the exponent matches. Okay. Then add the significant. That is add the significant part. Then normalize the result. Okay. So these are the 4 stages that should be crossed by an floating point operation. Okay. Now let us see how it will be done through one pipelined ALU and through one parallel ALU. Okay. Okay. So that is what in the previous slide we have discussed, right? Parallel ALUs and pipelined ALU. Now how this will be done in a pipelined ALU and in a parallel ALU, right? So let us assume there is only one ALU initially with respect to pipelined ALU, but let us assume this ALU contains 4 functional units where each can perform one task. There is one unit which can perform compare the exponent. There is another unit which can perform shift the significant. There is another unit which can be used to add the significant terms, and there is another unit which is used to normalize. Okay. So these are the different units we have, and this is the set of you have x and y on which you want to perform this operation, floating point operation. But x and y are not ordinary variables. These are vectors. X is a vector, y is a vector. Okay. Let us assume x contains 100 values and y contains 100 values. Okay. Now what does it mean? We want to perform arithmetic operation on x and y such that xi minus yi I want to store somewhere. Okay, that is x1 minus y1 x2 minus y2, x3 minus y3, up to x100 minus y100. Like this we want to do. Okay. So now, but we have only one ALU. So how are we going to do this effectively? So pipeline comes handy here. So first we take x1, y1. x1, y1 will just go where it will go to the compare stage. Okay. Then after compare it will go to shift stage. Okay. But when x1 and y1 are in shift stage, compare logic is free. So now x2 and y2 can use the compare logic. Okay. And after the second clock cycle, x1, y1 will leave the compare shift stage and they will enter into the add stage. Okay, now during the during the third clock cycle, x1, y1 entered into add stage. Now during the third clock cycle, x2 and y2 can use the shift stage, as shift stage is now free. Okay. Similarly, during the fourth clock cycle, x1 and y1 will leave the add stage and it will go into normalized state. Now, during the fourth clock cycle, x2 and y2 can use the add stage, so on and so forth. Okay. So now if you see 4 operations, this is 1, 2, 3, 4, 5. 5 operations are done in how many clock cycles? This is 1, 2, 3, 4, 5, 6, 7, 8 clock cycles. Within 8 clock cycle you are able to complete how many instructions? 5 instructions. Okay. So 6 instructions can be completed in 9 clock cycle. Okay. That is, the difference is only 3. The difference is only how many clock cycles? It is only 3 clock cycles. Are you getting? 7 instructions can be completed in 10 clock cycle. 8 instructions in 11 clock cycles. 9 instructions can be completed in 12 clock cycles. Okay. So if you keep on increase, 100 instructions can be completed in 103 clock cycles. There is no much difference. So when you increase the instructions, you see there is not much difference. 100 instructions you can complete in 103 clock cycles. It is as if you are it is as if you are doing parallelly, right? 1000 instructions can be completed in 1003 clock cycles. So as the number of instruction increases, the difference is decreasing. Are you getting? Okay. So this type of approach is called as pipelined approach. Okay. The next is a parallel ALUs. Okay. So with parallel ALUs, so now we have 4 ALUs. Let us assume the computer has 4 ALUs. ALU1, ALU2, ALU3 and ALU4. Now really you can perform 4 operations in parallel. Okay, really you can perform 4 operations in parallel. So now also assume that we have two vectors x and y. We want to subtract. But x is not an ordinary variable, it's a vector. It contains 100 items. Y contains 100 items. These are floating point numbers. We want to subtract it. Okay, large floating point numbers with exponent, all those things. So it has to go through all these operations: compare, shift, add and normalize. Okay. But anyway, we have 4 ALU, right? So what we are doing here, you just observe. Actually, this represents first ALU. Okay, I'll write here. This is ALU1. This is ALU2. This is ALU3. Okay. This is ALU4. Okay. So ALU1 is initially working on which instruction? X1, Y1. Okay. So we have X1, Y1, X2, Y2, up to we have X100, Y100. Up to we have X100 and Y100. So A1 is working on X1, Y1 initially. A2 is working on X2, Y2. A3 is working on X3, Y3. A4 is working on X3, Y4. Okay. Now this is the first clock cycle. You observe here, during the first clock cycle, A1, X1, Y1, X2, Y2, X3, Y3, X4, Y4. For all these four inputs, okay, X3, Y3, X4, Y4. For all these 4 inputs, the first task is done. What is first task? Compare is done. Compare is done. Are you getting? Compare is done. Now during the second clock cycle, all these 4 instructions, X1, Y1, X2, Y2, X3, Y3, all these things will enter into shift stage. All these things will enter into shift stage. Okay, now this compare stage is free. Please understand this. Here not only we are using parallel processing, we are using parallel processing with pipelining. Okay, we are not going to leave the advantage that we are going to get with pipelining. So we are going to use parallel processing and pipelining, right? So we are going to use parallel processing and pipelining. See this, how nicely it is designed. See, during one clock cycle, all these uh, instructions x1 y1 x2 y2 x3 y3 x4 y4, they completed the compare stage, so they are moving to shift stage. During the second clock cycle they entered the shift stage, but during second clock cycle, is this is free or not? Compare stage is free, so why should we leave it free? We have still more numbers, right? So during second clock cycle, when x1 y1 x2 y3 x2 y2 x3 y3 and x4 y4 are in shift stage, now we are what we are doing, x4 y4 x6 y6 x7 y7 x8 y8, that we are using it in compare stage. Are you getting? Are you getting? Now during, you see, during third clock cycle what happens, this x5 y5 x6 y6 x7 y7 x8 y8, all these will move to shift stage during third clock cycle. Okay, and also during third clock cycle what will happen, this x1 y1 to x4 y4, they will move to add stage. Okay, now compare is also free, shift is also free. Okay, now who will use compare? Now compare can be used by x9 y9 to x12 y12, and shift can be used by x4 y4 to x8 y8. Are you getting? During third clock cycle, shift is used by this x5 y5 to x8 y8, and compare is used by x9 y9 to x12 y12. Okay, see, now you see, now you see the degree of parallelism. See, because here we have 4 ALUs, and each ALU can provide 4 degree of pipelining. Okay, because they have each, I mean each ALU provides 4 stage pipelining. Okay, so there are how many functional units? Each ALU contains 4 functional units. Okay, so now it is as if you have 16 functional units. Totally you have how many functional units? 16 functional units, because there are 4 ALUs. So you have 16 functional units. Okay, so you can see here 12 operations were completed in just how many clock cycles? 4. This is 4, 5 and 6. 12 operations is completed in 6 clock cycles just. Okay, 4 operations completed in, I mean 4 operations were completed in 4 clock cycle. 8 operations were completed in 5th clock cycle. 12 operations were completed in 6th clock cycle. Okay, that is each clock cycle 4 operations is happening. Each clock cycle 4 operation is happening, right? Okay, only so for so in 7 clock cycles, in 7 clock cycles you will be finishing 10 operations. Okay, sorry, in 4 clock cycles 4 operations, 5 clock cycles 8 operations, 6 clock cycle 12 operations. Okay, 6 is 12, so 7th clock cycle another 4, 16 operations will be completed. Okay, right? 8 clock cycles 20 operations, 9th clock cycle 24 operations, so on and so forth. Are you getting? So at that rate it will perform the tasks. Okay, so this type of doing things is called as what? This type of doing things is called as uh, working with parallel processing, right? Here we have 4 parallel processor, and apart from parallel processing we are also using pipelining, right? Okay, so far whatever we have discussed is single control unit. So all these things have only single control unit. With we have discussed with uniprocessor, with pipeline. Uniprocessor is normal case, which is scalar operation, with pipeline ALU and with parallel ALU. Okay, but some see, so far we have not yet discussed parallel processing. In these two cases, this is pipeline, this is for parallel ALU, this is not parallel processing. Okay, of course here in this matrix example we assumed parallel processing, right? But you may also have parallel processing. That is, if you have multiple control units, then that is said to be having parallel processing. So when there are more than one control unit, Control unit is a part of a processor, right? So when you have multiple control unit, you can call it as a parallel processing system. So when there are more than one processors, we can call it as either a multi-processor system or a parallel processor system. So you may ask, what is the difference? The difference is, in a multi-processor system, if you have more than one processor, each processor will do a different job. They cannot coordinate and do a single job. Okay. But in a parallel processing environment, what happens in the sense, when you have multiple processors, all these processors can coordinate and they can do a one job also. But for that, there should be a proper coordination in hardware and software. So this is the difference between multi-processor and parallel processor. In multi-processor also you have different processors, more than one processor, but they cannot do one job in a coordinated way. If you have four different jobs, then you can assign each job to one processor. Let P1 do J1 job J1, let P2 do job J2, okay, let P3 do job J3, let P4 do job J4. Like that you can divide. These are individual tasks. They can do it. Okay. But if you assign for two processors one job, that they cannot manage. But in parallel processing environment, what happens in the sense, you have multiple processors, but you have only one job and you want all these processors to coordinate and to do it. You can do with parallel processing. Okay. That means there should be a proper coordination in the software and at the hardware level. So that is called as parallel processing. Okay. So that's the difference between parallel processing and multiprocessors. So why we are discussing here in the sense, for vector computation you can also use parallel processors, but not multiprocessors, because vector is what? It is only one thing, right? So we want to add A into B, okay, and store it in C. It is one entity. Now this one entity we may want to, if you have multiple processors, we may want to distribute the job to multiple processor, and it should be coordinated properly, right? So that can be done by parallel processors also. Okay. So that's it about vector computations. So with this we'll stop our discussion here. Okay. So with this the topic parallel processing also gets over, right? So in the next lecture we'll be moving to multi-core processors. We'll stop here. Thank you.